For decades, the name Bermuda Triangle has carried a strange weight. It evokes images of vanished ships, silent radios, planes that never reached their destination, and coordinates that seemed cursed. Stories passed down through books, documentaries, and whispered conversations have painted this region of the Atlantic Ocean as a place where logic breaks down, a place where compasses spin, time fractures, and reality itself appears to bend. And yet, beneath all the legends, beneath the sensational headlines and supernatural explanations, there has always been a deeper question left largely untouched. What if the Bermuda Triangle is not a mystery because it defies science, but because science has been looking in the wrong direction? What if the true explanation has been hiding in plain sight, not in myths or monsters, but in physics itself? Not in the supernatural, but in a phenomenon so subtle, so difficult to detect, that it escaped conventional measurement for decades. Imagine a force that does not announce itself with explosions or visible distortion, but works silently, relentlessly, altering trajectories, compressing space, and overwhelming human navigation systems without ever revealing its presence directly. Imagine a force that could explain every disappearance without invoking ghosts, aliens, or fantasy. This is where our investigation begins. The popular explanations for the Bermuda Triangle have followed familiar paths. Some claim methane hydrates rise from the ocean floor, creating massive gas bubbles that reduce water density and cause ships to sink. Others suggest rogue waves, violent storms, or sudden magnetic anomalies. Then there are the more sensational ideas: alien abductions, lost civilizations like Atlantis, time portals, or dimensional rifts. Each theory captures attention, yet none fully account for the consistency, scale, and historical spread of the incidents. Most importantly, none explain why modern technology, including satellites and advanced navigation systems, still reports anomalies in this region, even if disappearances have become less frequent. What if the problem is not that these explanations are entirely wrong, but that they are incomplete? What if they are secondary effects of something deeper, something far more fundamental, a hidden mechanism that does not destroy vessels outright, but disorients, destabilizes, and redirects them into catastrophe? A mechanism rooted in gravity itself. Gravity is the weakest of the four fundamental forces, yet it governs the largest structures in the universe. It shapes galaxies, bends light, and determines the movement of planets. We often think of gravity as constant and uniform, something we can rely on without question, but modern physics tells a different story. Gravity is not just a force, it is a curvature of spacetime, and where spacetime curves unexpectedly, reality behaves in unexpected ways. Over the past few decades, physicists have discovered that gravity is far from evenly distributed. There are gravitational anomalies across Earth's surface, subtle variations caused by differences in mass distribution within the planet. Mountains, deep ocean trenches, dense rock formations, and even variations in the mantle can create measurable deviations in gravitational strength. Most of these anomalies are small, detectable only with sensitive instruments, and harmless to everyday life. But what happens when multiple factors converge in one region, amplifying each other? The Bermuda Triangle sits atop a unique and complex geological structure. Beneath its waters lies a convergence of deep ocean trenches, ancient fault lines, and dense rock formations dating back millions of years. This region has experienced intense tectonic activity throughout Earth's history. Seismic surveys have revealed irregular mass concentrations deep beneath the ocean floor, far denser than surrounding areas. These formations alone could create localized gravitational distortions, but geology may only be one part of the equation. Earth is not a static object. It spins, it wobbles, and it interacts constantly with the gravitational pull of the moon and the sun. Tidal forces stretch and compress the planet's crust and oceans, creating subtle but continuous stress. In most regions, these forces balance out. In others, especially where geological irregularities exist, they can resonate. Think of it like pushing a swing. A single push does little, but repeated pushes at the right moment can create dramatic motion. Now imagine a region where Earth's internal mass anomalies, rotational forces, and tidal stresses align in just the right way. A region where spacetime curvature fluctuates rhythmically, forming a dynamic gravitational system rather than a static one. Not a black hole, not a singularity, but something far more subtle and far more dangerous to human technology. A gravitational vortex. The term vortex often brings to mind swirling water or violent storms, but in physics, a vortex simply refers to a region where a field exhibits rotational motion. There are vortices in fluids, in plasmas, and even in spacetime itself. Recent theoretical models suggest that under certain conditions, gravity can form localized rotational structures, especially when influenced by rotating masses and uneven density distributions. These structures would not look dramatic. They would not tear ships apart or visibly distort the ocean. Instead, they would gently but persistently alter trajectory. A vessel entering such a region would experience conflicting gravitational vectors. Instruments calibrated for uniform gravity would begin to fail, not because they are broken, but because the environment no longer matches their assumptions. Gyroscopes would drift. Compasses would show slight but increasing Pilots and captains would correct course again and again, unaware that each correction is leading them further into instability. This could explain one of the most puzzling aspects of Bermuda Triangle incidents: the lack of distress signals. Crews did not report storms, attacks, or mechanical failures. Instead, communication often became confused, disoriented, or abruptly silent. In some recorded cases, pilots reported that everything looked normal, yet their instruments were behaving strangely. These reports have often been dismissed or attributed to human error. But what if they were accurate descriptions of a physical phenomenon we did not yet understand? Consider the famous Flight 19 incident in 1945. 5 U.S. Navy training planes vanished during a routine exercise. The weather was clear. The pilots were experienced, yet they became increasingly disoriented, reporting that their compasses were malfunctioning and that they could not determine their position. Rescue planes sent after them also disappeared. Official explanations pointed to navigation errors, but even today, many details remain unresolved. If a gravitational vortex existed in the region, it would not pull objects downward like a black hole. Instead, it would create lateral distortions, warping perceived distance and direction. A plane flying straight could unknowingly curve off course. Fuel calculations would become meaningless. Search and rescue operations would be compromised by the same distortions, explaining why recovery efforts often failed. Modern satellite data has added another layer to this mystery. High-resolution gravity mapping missions, such as GRACE and GOCE, have revealed unexpected gravitational variations over the Atlantic, including anomalies near the Bermuda Triangle. These variations are subtle, measured in microgals, but they are persistent. While mainstream explanations attribute them to ocean currents and seafloor topography, some researchers argue that these factors alone cannot account for the observed fluctuations. Even more intriguing are reports of transient gravitational spikes, short-lived anomalies that appear and disappear, seemingly synchronized with tidal cycles or solar activity. These spikes are difficult to study because they do not last long and require precise timing to detect. But if they are real, they could represent moments when the gravitational vortex intensifies, becoming particularly dangerous to navigation. This brings us to a crucial point. The Bermuda Triangle may not be dangerous all the time. It may only become hazardous under specific conditions, when multiple forces align. This would explain why modern shipping lanes and flight paths pass through the region without incident most of the time, yet anomalies still occur. It would also explain why historical disappearances seem clustered in certain periods. Throughout history, humans have struggled to accept explanations that challenge intuition. Before germs were discovered, disease was blamed on curses or bad air. Before plate tectonics, continents drifting was considered absurd. Today, gravity vortices may sound equally implausible, but science advances by questioning assumptions, not by clinging to comfortable narratives. What makes this theory particularly compelling is that it does not require rewriting physics. It builds on existing principles of general relativity, geophysics, and fluid dynamics. It suggests that under rare but natural conditions, gravity can behave in complex, localized ways that we are only beginning to detect with modern instruments. As we move deeper into this investigation, we will examine the data that supports this hypothesis. We will look at satellite measurements, naval reports, and experimental models that reveal patterns previously overlooked. We will explore how energy flows through Earth's crust and oceans, and how these flows might interact with gravity itself. Most importantly, we will confront the uncomfortable possibility that the Bermuda Triangle is not a relic of superstition, but a warning. A warning that our understanding of Earth is still incomplete. That beneath the surface of familiar oceans, forces are at work that challenge our assumptions about safety and predictability. Forces that do not announce themselves but quietly reshape reality. If this invisible gravitational vortex exists, it changes everything. It means that the Bermuda Triangle is not a mystery to be dismissed, but a phenomenon to be studied with urgency. It means that the disappearances were not random tragedies, but interactions with a hidden aspect of our planet. And it means that similar anomalies could exist elsewhere, waiting to be discovered. As we continue, ask yourself this question. If gravity itself can twist and turn in ways we have barely begun to measure, what else might be hidden in the fabric of our world? And how many mysteries labeled as myths are simply science waiting to catch up? Stay with us, because what comes next will challenge not only what you believe about the Bermuda Triangle, but what you believe about reality itself. The moment a theory moves from speculation into measurement, everything changes. Stories become data, anecdotes become patterns, and the Bermuda Triangle, long treated as a cultural curiosity, begins to reveal something far more unsettling when examined through this lens. Once researchers stopped asking whether something supernatural was happening and instead asked whether something measurable was being missed, a new picture began to form. One of the most overlooked sources of information comes from gravity mapping satellites. Missions such as GRACE and GOCE were designed to study Earth's gravitational field with unprecedented precision. Their primary purpose was to track changes in ice mass, ocean circulation, and Earth's internal structure. They were not searching for mysteries, and yet, buried within their datasets are irregularities that refuse to fully conform to conventional explanations. Across the Atlantic, gravity measurements reveal a patchwork of subtle anomalies. Most align neatly with known geological features. But within the general coordinates associated with the Bermuda Triangle, researchers have noted fluctuations that appear inconsistent in both magnitude and timing. These are not constant anomalies, like those caused by mountain ranges or deep trenches. Instead, they seem to pulse. They strengthen and weaken over time, sometimes correlating with tidal forces, sometimes with geomagnetic activity, and occasionally with no obvious trigger at all. This variability is crucial. A static gravitational anomaly would be easy to model and adapt to. Navigation systems could be calibrated around it, but a dynamic anomaly, one that shifts in intensity and orientation, introduces chaos into systems designed for stability. This kind of environment is especially dangerous for vehicles moving at high speed, such as aircraft. Pilots rely on a combination of instruments that assume gravity behaves predictably. Gyroscopes depend on inertial stability. Altimeters assume consistent gravitational acceleration. Even GPS systems, while extraordinarily precise, must constantly correct for relativistic effects related to gravity. These corrections are based on global models, not localized, rapidly changing distortions. A sudden, transient deviation could create discrepancies large enough to confuse onboard systems without triggering obvious failure warnings. Naval records provide additional insight. Declassified logs from the mid-20th century describe incidents in which ships experienced inexplicable navigational drift. Crews reported that they were correcting course repeatedly, only to find themselves further off track. In some cases, multiple ships traveling together reported similar deviations simultaneously, ruling out individual instrument malfunction. At the time, these reports were often attributed to strong currents or human error. But when overlaid with modern gravity data, something unusual emerges. Many of these incidents occurred during periods when satellite data now suggests heightened gravitational fluctuation in the region. This correlation does not prove causation, but it raises uncomfortable questions about how much was missed simply because the tools to measure it did not yet exist. Oceanographic data adds another layer. The Bermuda Triangle sits at the intersection of powerful ocean currents, including the Gulf Stream. This current alone can affect navigation, but it also contributes to mass redistribution on a massive scale. Billions of tons of water move continuously through this region, altering local gravitational conditions. Normally, these changes are smooth and predictable, but when combined with uneven seafloor density and tectonic stress, they may create feedback loops. Imagine a system where moving water amplifies an underlying gravitational irregularity, which in turn subtly alters the flow of that water. Over time, this interaction could produce rotating gravitational patterns, not unlike atmospheric vortices, but invisible and far more difficult to detect. Such a system would not be violent in the traditional sense. It would not produce towering waves or visible destruction. Instead, it would quietly bend paths, misalign instruments, and erode situational awareness. This brings us back to one of the most haunting features of Bermuda Triangle incidents: confusion. Pilots reporting that they could not tell which direction they were flying. Captains stating that familiar stars no longer aligned with expected bearings. Radio operators describing voices that sounded calm but disoriented, as if the speakers themselves did not realize the danger they were in. In one lesser-known incident from the 1960s, a commercial vessel reported that its entire navigation suite began to drift simultaneously. Not fail, drift. The compass slowly rotated. The gyro compass disagreed with the magnetic compass. Celestial navigation produced conflicting results. Weather was calm, visibility was clear. The ship did not disappear, but it exited the region hundreds of miles off its intended course, with no clear explanation. Such cases rarely make headlines because they lack drama, but scientifically they are more valuable than disappearances. They represent near misses, moments when a vessel encountered something abnormal and survived long enough to report it. When these reports are analyzed collectively, patterns emerge that are difficult to ignore. Another key factor is time perception. Several pilots and sailors have reported strange distortions in perceived time while traversing the region. Clocks running slow or fast. Flight durations that did not match fuel consumption. While these claims are controversial, they align intriguingly with relativistic effects predicted by general relativity. Gravity affects time. Stronger gravitational fields slow time relative to weaker ones. Even small variations can be measurable with atomic clocks. Modern experiments have confirmed that clocks at different altitudes tick at different rates. Satellites must correct for this constantly. If a localized gravitational anomaly existed, especially one that fluctuated, it could introduce temporary time discrepancies. These would not be dramatic enough to create science fiction scenarios, but they could contribute to confusion, miscalculation, and error accumulation. Critics often argue that if such a phenomenon existed, it would be widely recognized by now. But this assumes that scientific discovery is instantaneous and evenly distributed. In reality, many phenomena are understood only after decades of incremental evidence. Plate tectonics faced resistance for nearly half a century. Ball lightning was dismissed as folklore until systematic observation forced reconsideration. The gravitational vortex hypothesis suffers from a similar problem. It exists at the intersection of multiple disciplines. geophysics, relativity, oceanography, and navigation science. No single field is responsible for studying it in isolation. As a result, evidence remains fragmented, scattered across data sets collected for entirely different purposes. Recent computer simulations have begun to bridge this gap by modeling Earth's mass distribution in high resolution and simulating tidal forces over time. Researchers have observed the emergence of rotating gravitational gradients in specific configurations. These gradients are weak, but when extended over large areas, they can influence motion significantly. Importantly, these models show that such gradients are highly sensitive to initial conditions, meaning they can appear and disappear unpredictably. This unpredictability matches historical records remarkably well. Periods of intense activity in the Bermuda Triangle appear clustered, followed by long stretches of relative calm. This would be expected if the underlying mechanism requires precise alignment of multiple factors. It also explains why attempts to deliberately study the phenomenon often fail. By the time researchers arrive with instruments, the conditions may have already changed. Another compelling piece of evidence comes from magnetometer data. While gravity and magnetism are distinct forces, they often interact indirectly through Earth's internal dynamics. Some incidents report simultaneous magnetic and navigational anomalies. This has traditionally been explained as magnetic disturbance causing compass errors, but magnetic anomalies alone cannot account for inertial drift or time discrepancies. The gravitational anomaly, however, could influence both systems indirectly. Changes in mass distribution affect Earth's magnetic field. At the same time, gravity directly affects inertial systems. This dual influence could create the illusion of a purely magnetic problem, masking the deeper cause. Perhaps the most sobering implication of this research is that the Bermuda Triangle may not be unique. It may simply be the most famous example of a class of phenomena that exists elsewhere on the planet. Smaller, less intense gravitational vortices could exist in other regions, influencing weather patterns, ocean currents, or even seismic activity without being recognized for what they are. If this is true, then the Bermuda Triangle is not an anomaly in isolation. It is a window, a place where conditions are extreme enough to reveal something fundamental about how our planet works, something that challenges our assumption that gravity is smooth, stable, and predictable at human scales. As we move forward, the question is no longer whether the Bermuda Triangle is real. The question is what it represents. Is it a rare natural hazard, like a volcanic hotspot or an earthquake zone? Or is it evidence of a deeper complexity in Earth's gravitational behavior that we have yet to fully grasp? In the next part of this investigation, we will examine how modern technology, including autonomous sensors and deep-sea instruments, is beginning to test these ideas directly. We will look at experimental data, emerging theories, and the growing debate within the scientific community. And we will confront the possibility that understanding the Bermuda Triangle may require us to rethink not just navigation, but the very nature of gravity on Earth. Stay with us, because the closer we look, the clearer it becomes that this is not a story about disappearance. It is a story about discovery. As technology advances, mysteries that once relied on anecdote begin to leave measurable fingerprints. Over the last 2 decades, a quiet shift has taken place in how scientists observe Earth's most inaccessible regions. Autonomous sensors, deep-sea probes, and satellite-linked instruments now operate continuously, collecting data in places humans rarely visit. And it is within this new generation of observation that the Bermuda Triangle begins to reveal patterns that were previously invisible. One of the most significant developments has been the deployment of autonomous ocean gliders. These machines travel slowly through the water column, adjusting buoyancy rather than using propellers, allowing them to operate for months at a time. They measure temperature, salinity, pressure, and subtle changes in acceleration, while their primary mission is climate research. Several gliders operating near the Western Atlantic have recorded anomalies that do not fit standard oceanographic models. In multiple datasets, researchers noticed unexplained deviations in vertical acceleration. These were not associated with turbulence, currents, or mechanical malfunction. The readings appeared sporadically, lasted only seconds to minutes, and then vanished. Individually, such anomalies could be dismissed as noise, but when mapped geographically, a clustering effect emerged. Many occurred within or near the traditional boundaries of the Bermuda Triangle. At the same time, deep-sea gravimeters placed on the ocean floor began reporting microvariations in gravitational strength that exceeded predicted models. These variations were small, but they exhibited a rotational signature, instead of increasing or decreasing uniformly. The gravitational vector appeared to shift direction slightly over time, as if tracing a slow, invisible spiral. This is where resistance within the scientific community becomes apparent. Gravity is one of the most rigorously tested aspects of physics. Any claim of unusual gravitational behavior invites intense scrutiny, and yet the data persists, not loudly, not dramatically, but quietly, consistently enough to provoke debate among those who encounter it. Some researchers argue that these readings are artifacts, the result of instrument sensitivity exceeding practical limits. Others suggest unknown interactions between ocean pressure and sensor calibration. These explanations are not unreasonable, but they share a common feature. They attempt to fit the data into existing frameworks rather than asking whether the framework itself might be incomplete. Meanwhile, aerospace data offers an entirely different perspective. Modern aircraft continuously record vast amounts of telemetry, while most of this data is proprietary or classified. Some anomalies have surfaced through accident investigations and voluntary reporting systems. Pilots flying through the Western Atlantic have occasionally reported inertial discrepancies that resolve once they leave the region. In several documented cases, aircraft inertial navigation systems required manual realignment after transiting specific coordinates. The systems did not fail outright. Instead, they accumulated small errors faster than expected. These errors were not consistent with wind shear, turbulence, or magnetic interference alone. Again, the explanation offered was often sensor drift, but sensor drift typically occurs gradually and predictably. What was observed here was episodic and location-dependent. Even more intriguing are reports involving unmanned aerial vehicles. Drones lack human perception, eliminating psychological factors like stress or disorientation. Yet some long-range UAVs operating over the Atlantic have logged unexplained navigation corrections and transient signal degradation in regions overlapping the Bermuda Triangle. Because these platforms rely heavily on inertial data when GPS signals fluctuate, they are particularly sensitive to gravitational inconsistencies. If a localized gravitational vortex exists, this is precisely how it would manifest. Not as catastrophic failure, but as a growing mismatch between expectation and reality. Systems would compensate automatically, unaware that their underlying assumptions no longer hold. This brings us to a controversial but unavoidable topic: why this phenomenon has not been publicly acknowledged. The simplest answer is not conspiracy, but fragmentation. Data relevant to this question is scattered across civilian research, military operations, commercial aviation, and academic institutions. No single entity sees the full picture. Each anomaly viewed in isolation appears insignificant. There is also the issue of liability. Acknowledging a natural hazard that affects navigation unpredictably raises difficult questions. How do you regulate airspace or shipping lanes around a phenomenon that cannot be reliably forecast? How do you assign responsibility for incidents that occur within it? Silence, in this context, becomes a form of risk management. Historically, similar patterns have occurred. Early warnings about ozone depletion were initially downplayed. Seismic risks in certain regions were underestimated until catastrophic events forced re-evaluation. Science does not progress linearly. It advances through tension between evidence and acceptance. The gravitational vortex hypothesis sits precisely at this tension point. It does not violate known laws of physics, but it challenges assumptions about scale and stability. It suggests that gravity, while weak, can organize itself into complex structures under the right conditions. Structures that are transient, localized, and difficult to measure, but real nonetheless. Some experimental physicists have begun exploring analog systems to better understand this possibility. In laboratory settings, rotating fluids with uneven density distributions can produce persistent vortices that influence objects moving through them. While gravity cannot be replicated directly in such experiments, mathematical analogs show that fields with similar properties can create non-intuitive trajectories. In these models, objects entering the field do not experience a sudden force. Instead, they are gently guided along curved paths. The longer they remain, the stronger the deviation becomes. This mirrors reports from the Bermuda Triangle, where prolonged exposure seems more dangerous than brief transit. Another striking implication is energy transfer. A gravitational vortex would not consume energy like a black hole. It would redistribute it. This could explain reports of sudden electrical anomalies, drained batteries, or unexpected system resets. Energy moving through a distorted space-time geometry behaves differently, even if the effect is subtle. Some skeptics point out that if such a phenomenon existed, it would have implications beyond navigation, and they are right. A persistent gravitational anomaly would influence ocean circulation, atmospheric patterns, and possibly even biological systems. Interestingly, the region does exhibit unusual weather behavior and ecological patterns, though these are usually attributed to the Gulf Stream. Once again, the question arises: are these separate phenomena, or interconnected expressions of a deeper process? The more data is examined, the harder it becomes to dismiss the possibility that the Bermuda Triangle represents a natural laboratory for studying complex gravitational behavior, a place where Earth's rotation, internal structure, and external forces interact in a way that is rare but not impossible. This realization reframes the entire narrative. The disappearances were not evidence of hostility or malevolence. They were encounters with something indifferent, a system that does not target humans, but does not accommodate them either. Nature, operating beyond our expectations. Understanding this does not make the phenomenon less unsettling. In some ways it makes it more so. Supernatural explanations can be dismissed. Physical ones must be confronted. If gravity itself can organize into structures that challenge navigation and perception, then human mastery over the environment is more fragile than we like to believe. Our technology works because the universe is predictable enough. The Bermuda Triangle suggests there are places where that predictability breaks down. As we approach the final part of this investigation, we will confront the broader implications of this discovery, what it means for future exploration, how it could change our understanding of planetary physics, and why the Bermuda Triangle may be the first recognized example of a phenomenon that exists far beyond Earth. Because once you accept that gravity can twist, rotate, and fluctuate in localized ways, a far more profound question emerges. If this can happen here, on our own planet, what might be happening elsewhere in the universe? Stay with us. The conclusion does not close the mystery, it opens something far larger. When a mystery survives this long, it is not because the truth is unreachable, but because the consequences of understanding it are uncomfortable. The Bermuda Triangle has endured not because it is inexplicable, but because its implications reach far beyond ships and planes. If the phenomenon we have explored is real, then it forces a re-evaluation of how stable our world truly is. Gravity has always been treated as the most reliable constant of human experience. It is the force we trust implicitly. We build our cities, our machines, and our calculations on the assumption that it behaves the same way everywhere, all the time, and for the most part it does. But history has shown that nature often hides its complexity beneath layers of apparent simplicity. The emerging picture suggests that the Bermuda Triangle is not an anomaly in isolation, but an extreme case of a broader principle. Gravity, while globally predictable, may exhibit localized complexity under certain conditions that involve rotation, mass imbalance, resonance, and external forcing. When these elements align, gravity may not simply pull downward, it may twist, circulate, and fluctuate in ways that subtly undermine human systems. This does not require exotic physics or speculative dimensions. It arises naturally from general relativity, combined with Earth's dynamic interior and external influences. The planet is not a rigid sphere. It is a layered, rotating, vibrating system constantly shaped by internal heat and cosmic forces. Within such a system, complexity is not an exception. It is inevitable. The Bermuda Triangle then becomes a boundary zone, a place where the assumptions built into our technology encounter conditions they were never designed to handle. Navigation systems assume linearity. Instruments assume uniformity. Human perception assumes consistency. A gravitational vortex violates all three, not violently but persistently. This helps explain why the phenomenon feels elusive. There is no single dramatic event to point to, no catastrophic explosion, no unmistakable signature. Instead, there is erosion. Small errors accumulate, orientation degrades, confidence fades, decisions are made based on data that is subtly wrong. And by the time the situation becomes critical, the opportunity for correction has already passed. Seen through this lens, the historical accounts take on new meaning. The calm voices in distress calls, the lack of visible damage, the absence of wreckage. These are not signs of fantasy. They are signatures of a system failure rooted not in machinery, but in physics. And perhaps most unsettling of all, this understanding suggests that the Bermuda Triangle has never been turned off. It has simply been quiet. Modern technology, improved forecasting, and altered routes may have reduced exposure, but the underlying conditions remain. They fluctuate. They wait. This realization raises critical questions for the future. As autonomous vehicles become more common, as shipping relies increasingly on algorithmic navigation, and as aviation pushes further into automation, the margin for unpredictable physical environments narrows. Systems without intuition, without improvisation, may be even more vulnerable to subtle anomalies. If gravity itself can deviate from expectations in localized regions, then future exploration, both on Earth and beyond, must account for this possibility. Other planets, with different internal structures and rotational dynamics, may host similar or even more extreme phenomena. Moons with subsurface oceans, gas giants with immense mass differentials, even exoplanets orbiting close to their stars. What we are seeing in the Bermuda Triangle may be a scaled-down version of processes that operate throughout the universe. Gravity shaping not just orbits but environments. Not just paths but outcomes. There is also a philosophical consequence. Humans have long divided the unknown into two categories, the supernatural and the scientific. When something resists explanation, it is often pushed into the former. The Bermuda Triangle lived there for decades, but, as history has shown repeatedly, the supernatural often retreats as science expands. This does not make the universe less mysterious, it makes it more profound. A gravitational vortex is not less awe-inspiring than a myth. It is more so, because it is real. It exists not to frighten us, but to remind us that understanding is always provisional. The resistance to this idea is understandable. Accepting it means accepting that our mastery of nature is incomplete, that there are forces we navigate daily without fully comprehending them, that safety is not just a matter of engineering, but of humility. And yet, this is precisely how progress occurs, by confronting uncertainty rather than avoiding it, by following evidence even when it leads to uncomfortable conclusions. The Bermuda Triangle, stripped of legend, becomes something far more valuable than a mystery. It becomes a case study, a warning, and an invitation, a warning that Earth still holds physical processes we do not fully understand. an invitation to look closer, measure deeper, and question assumptions we take for granted. Because once you recognize that gravity itself may behave in complex, localized ways, you begin to see the world differently, not as a static stage on which events unfold, but as an active participant, a planet that moves, responds, and occasionally surprises us. The ships and planes that vanished were not taken by malice or magic. They encountered a reality that did not match their expectations. And that, perhaps, is the most important lesson of all. Mysteries do not exist to frighten us. They exist to reveal the limits of our knowledge. The Bermuda Triangle has always been telling us something. Not about monsters or curses, but about physics, about Earth, about how much we still have to learn. And as science continues to peel back the layers, one thing becomes clear. The real mystery was never why things disappeared. It was why we stopped asking the right questions. If this exploration challenged the way you see the world, stay curious, because the most dangerous assumption is believing we already understand everything. And if you want to continue exploring the hidden forces shaping our reality, this is only the beginning.